Here's an example of an ice problem. 1.5 moles of oxygen, 2 moles of sulfur dioxide, and 3 moles of sulfur trioxide are placed in a 1-liter reactor. When the reaction reaches equilibrium, the mixture contains 3.5 moles of sulfur trioxide. What is the value of Kc for this reaction? So, how do we know whether this is an ice problem or not? Well, if we read the problem, it tells us that this amount, and this amount are placed in a reactor. That is an initial condition. That is not an equilibrium condition. Then we're told that it does reach equilibrium and the mixture contains 3.5 moles of SO3. So we do know something. We know one of the amounts at equilibrium, but we don't know all of them. So in order to find Kc, we're going to need to know all of them. So how are we going to do this? Well, I guess before I go too far, I just want to point one thing out really quickly here. Notice that all of the amounts that they give us are in moles. Moles are not an acceptable unit to plug into a K, an equilibrium expression. Fortunately, though, they have made the problem easy for us by making it a 1-liter container. So when we divide by the volume, we'll still be working with the same numbers. So 1.5 moles in a liter is 1.5 molars. So we actually don't need to do any changes on those numbers. So let's go ahead and see. We do need an ice chart because there's some discrepancy. We know the initial, but not all the final. So let's go through and start our ice chart. So we start with an initial value. There's going to be a change, and then at equilibrium we have something. So we're going to split this up like that. And initially, if we go back to the problem, it said that the moles of SO2 was 2 moles, which is 2 molars because it's per 1 liter. The oxygen amount was 1.5, and the sulfur trioxide was 3. So those are our initial amounts. It doesn't tell us any of the changes, and it does tell us a little bit about equilibrium. It tells us that at equilibrium we have 3.5 moles of SO3. So we have 3.5 moles here. So if you're clever now, you already can kind of see that this is going to be a pretty quick and easy problem because we know the change, don't we? We know it went from 3.0 molar to 3.5 molar, so that's a change of positive 0.5. There's 0.5 added to the SO3 number there. And since this change row has to be related stoichiometrically by these coefficients, we can kind of do like we would with stoichiometry. So this is kind of our A number. We know this amount. That's a known, and these are not known. So we can think of this as A and this is B. So what do? We do moles of A times, and it's going to work for molarities also. So take it times coefficient of B over coefficient of A. So this is going to be 0.5 is our molars of A. We're going to multiply that by if we're going to do the oxygen, it's going to be the coefficient of 1 over 2, which is 0.25. And you got to think about the sign here. If you're making this, then you must be using this, so that's going to be a negative value. Now, if you don't like all this B over A stuff, you can do this a little bit more intuitively if you just think, well, for every one of these, you have to make 2 of these. For one of these used, so this number has to be twice as big as this number. So that's where this number ended up being half. By the same argument, our coefficients here are the same, so these are used and made up at the same rate. So this number and this number need to be the same, negative 0.5, or if you want to do the coefficient argument, it'd be 0.5 times 2 over 2 is 0.5 again. Reactants are going to lose, products are going to make, so we got to be careful with our signs. And so there you go. At equilibrium, we now know how much of everything we have at equilibrium. It's 2 minus a half is 1.5. 1.5 minus 0.25 is 1.25. And it already told us that number. And so there we have our equilibrium amounts, and now we can plug those into our K expression. Our K expression is going to be, we never did write our K expression yet, did we? We should. So our Kc expression, since we're using molarities, is going to be SO3 squared. These are equilibrium, so brackets mean molarity at equilibrium. SO2 squared and O2. So if we go ahead and plug all those numbers in that we just derived, we have the SO3 number is 3.5. The SO2 number is 1.5. We're going to square that. And then the O2 number is 1.25, not going to be squared. And that's going to spit out our answer, which is what it was asking for. All this problem asked for was the K, so 3.5 squared divided by 1.5 squared divided by 1.25 spits out an answer. I say spit a lot, don't I? Of I don't remember how many sig figs. Let's call it 2 sig figs. So Kc is going to be 4.4